Hello, and welcome to graphing linear inequalities with two variables. This is a part of an Algebra 1 series I've been doing where we're right now in Unit 4 talking about linear inequalities in general. We've graphed them on a number line, we've graphed a variety of them from simple to complex and added compound inequalities, and now we're going to say, okay, how can we relate this to what we did where we were graphing lines on a coordinate plane? Is there a way to somehow make those into inequalities? And of course there is. So two variables now instead of one, so it must be twice the fun. Yeah. So let's go ahead and do a nice warm-up here. We're going to graph the following equation on this coordinate plane. So just to remind you how we do that, hopefully it hasn't been super long since you did this, and hopefully it's not too hard to remember. This is in slope-intercept form, which is y equals mx plus b. And so when we're in y equals mx plus b, the number in front of x is telling us our slope, and the number that's being added or subtracted is telling us b, which is our y-intercept. We begin with b, so we put a dot at 3 on the y-axis, and then we're going to use our slope, which is 1/2, to do the rise over the run. So those are both positive because it's a positive 1/2, or they could both be negative since it's a positive 1/2. So we're going to rise 1 and run 2 to the right. And then we're going to draw this line. How convenient that my ruler is already at this nice angle. So here is our line. Now, really quickly, what is this line even showing us? This line is showing us the collection of points that give us solutions to the equation we started with. So if we pick out a point on this line and plug it into y equals 1/2 x plus 3 for x and y, what we should get is a true statement. If we pick a point that's not on the line and we plug it in, we should get something that's not true. So for instance, we could pick out this point 2, 4, and we could say 4 equals 1/2 times 2 plus 3. And we could say, is this a true statement? Well, 1/2 times 2 is 1, because the 2's cancel. And that's 1 plus 3, which, yeah, that does equal 4. So that's a point on the line that gives us a solution to this equation. If I pick any point that's not on the line, which we could go really easy here and pick 0, 0, and I plug that in, I should get something that's not true. So 0 equals 1/2 times 0 plus 3 would be, this part would be 0. 0 plus 3 is 3. Is it true that 0 equals 3? No. So that's why 0, 0 is not on this line, is because that's not something that actually works for this equation. Now, let's think about how we can put inequalities into this situation. What would it mean if instead of having y equals 1/2 x plus 3, what would it mean if instead we had y equals, or not y equals, what would it mean if we instead had y is less than 1/2 x plus 3? Then what could our solution look like? And so just to kind of point this out, we've been dealing with one variable and one dimension. So we've only been concerning ourselves with left and right on a number line, but now we're going to be talking about two variables, which means two dimensions. So we'll have a left and a right and an up and a down. So all of a sudden, what was relatively easy to figure out, left and right being less than and greater than, now we've got to come up with, how do we say less than or greater than when we have more directions? And so that's going to be probably part of the trickiness of these types of problems. Just think about having this problem here, x plus y is greater than 4, and we can probably come up with some answers to that work, right? Pretty easily, actually, because any two numbers you pick that you add together and they're bigger than 4 would give you a set of points, like 2, 6. 2 and 6 add up to be 8, that's bigger than 4. We could do -10, 15. Those numbers add up to be greater than 4. We can do that actually for infinitely many points. So this is going to look a bit different when we're done with it. I'm going to show you how we basically convey to people what our solution is whenever we've got an inequality. Let's look at example 1 here. And these are actually coordinate planes that we're going to graph on, even though we actually only have one variable. So first step is to remember, how do I graph something like x equals -2? And then think about, okay, what does that mean for us having an inequality? How do I relate this? So if we remember back to what x equals -2 looked like, it does not fit into slope-intercept form, which is because its slope is undefined, and an undefined slope comes with a vertical line. So when we see something like x equals -2 or x is less than -2, we should be putting a dot at -2 on the x-axis and then drawing a vertical line. But this is not equal to. We have x is less than -2, not equal to. We need a way to convey to somebody that the things that are on the line itself are not a part of our solution. So instead of doing a normal line, we're going to do a dotted line or a dashed line. Basically a line that's broken. And that's going to show people that, hey, what's on this line is not part of our solution. It's typically called a dotted line, but I always make dashes instead of dots. And I think most people do. So that's why you'll hear me say dotted or dashed. Because I like to make dashed lines. I think they look pretty nice. Now, x is supposed to be less than -2. So just like on our number line, how we shaded, we're going to shade on our coordinate plane. But basically, our coordinate plane is divided up into two parts, the left side and the right side, by this vertical line. So we need to figure out which side of this gives us points that fit, which side of this gives us points that have an x value less than -2. Is it over on the right, where we've got numbers like x numbers like 1, 2, 3, 4, 5, or is it on the left, where our x values are -3, -4, -5? It's on the left. So when we do when we do inequalities that just have an x, but we put them on the coordinate plane, it actually is kind of really similar to what would happen if we were on a number line, because since this is less than, we're going to shade to the left. Now, my shading looks a lot better whenever I do it on paper than on the computer. I really like shading on paper with a pencil, personally. Now, be careful here as you're shading that as you get close to your dotted line, don't accidentally make your dotted line look filled in or like a normal line. That can happen. Don't do that. But here's our answer. We were asked to sketch x is less than -2. We've got a vertical line at -2. It's dashed to show it's not equal to, and we've shaded to the left because we wanted all of the points where our x value is less than -2. Let's try on the right side of this page, y is greater than or equal to 4. So in this case, we can think of this in slope-intercept form, even though there's not an x. If we do, we have to say, okay, this is like there's a 0x. And that's helpful because then we're thinking about a zero slope. A zero slope is a horizontal line. And so then we can go, oh yes, I remember, y equals 4 is a horizontal line at 4. Now, whenever we were not equal to, we made a dashed line. When we're equal to, we're just going to make a normal line. So I'm going to draw a normal line, normal horizontal line, left and right here, that this is the line y is equal to 4. But what we want to do is add to this the idea that y can be greater than 4. So which direction makes sense for that? Would that be the numbers that are below the line, like 3, 2, 1? Are those the numbers that are greater than 4? Or would it be numbers above the line, like 5, 6, 7, 8? You're right. It would be the numbers above the line. I may be watching too much children's TV because I'm about to start being like, what's the answer? And then like waiting for you to respond, and then, you know, like I'm thinking of Blue's Clues. You know, put it in your notebook because they're Blue's Clues, Blue's Clues. Okay. So that's example 1. We're going to do a couple more like this just to make sure we've got it. Example 2. Same kind of situation. We've still just got one variable, so these are either vertical or horizontal lines. We'll add to our complexity in the next example, don't you worry. So we're going to sketch the graph of y is less than or equal to -3. So I'm going to put a horizontal line at -3. Hopefully at this point you are able to remember which lines are horizontal and which lines are vertical. If not, that's something that you need to work on memorizing. Y is less than or equal to -3. We're going to shade below because those are the numbers where y would be more negative, which is what less than means in this case. My line was solid. I don't know if I said that. My line is solid because it's equal to. It just so happened that these two that I picked that were y were equal to, and now the two x's are not equal to. That's just a coincidence. Okay, so we decide whether to do a solid line or a dashed line based on whether the inequality is equal to or not equal to. So for the second one on here, x is greater than 1, we're going to put a dashed line because we're not equal to. It's a vertical line because it's x is greater than 1. And we think, where are the numbers for x that are greater than 1? Are they to the left or are they to the right? And then we go to the right, to the right, to the right, to the right for our answer. So there we go. Now let's add to this actually having two variables. So we want to sketch y is less than -x plus 4. This is in slope-intercept form, which is nice and handy. Let's take a moment to say, okay, it's not equal to. So when we do draw our line, it's going to be dashed. It's really easy to forget that step and to draw a solid line and then either to get it wrong or to realize that you did it wrong and then have to like try to erase or whatever. So try to think about that early on, that this is going to be less than because it, and not equal to, so it's going to be a dashed line. So we need our y-intercept, which is the +4. We need our slope, which is -1, which we're going to turn into -1/1, or +1 over -1, whichever one you want to use. We're going to go down 1, right 1. We can do a bunch of points or we can do a few. Really, because this is supposed to be a dashed line anyway, we could just put a bunch of dots and that makes it a dotted line, right? But like I said, I like dashed better than dots. So something like this. That is just supposed to convey to somebody that, hey, anything on this line is not a solution. So 0, 4, which is on this line, doesn't actually work out to be a solution. It almost does. It would if it was equal to, but it doesn't. Now, it can be tricky to know where to shade because just like before, this is split into two parts, although it's like a bottom left and a top right part. So we think about, how do I convey that y is less than -x plus 4? And I've got a really, really good trick to help you with that. Here's what you do. You take your pen or pencil and you put it on the line that you've got drawn. Doesn't matter where you put it, you're just going to place it on there. And then if your inequality is less than, you draw down. If your inequality is greater than, you draw up, because this is y is less than or y is greater than. And then whatever side of the line you've drawn on, that's the side we should shade. So let me show you how that works. I put my pen on the line. I say this is less than, so I'm going to draw down. And then I can go, okay, which side of the line did I just draw on? That's the side that I'm going to shade. So this is the side that is less than. Now, I imagine some of us are probably going, well, of course that's the side that is less than. And for others, we're going, I have no idea why that's the side that's less than. I think in particular, there's a certain type of line that can be particularly tricky, that is like almost straight up and down, but not quite, and it can be hard to know which way we're supposed to shade it. So this will always work, this trick that I've given you. As long as it's got y, you can either draw up for greater than or down for less than, and it'll show you what side you should be on. So we'll just do some more examples to make sure that this is working. At some point, if you're not working ahead, you should at least be trying to guess what's happening, like guess which side should be shaded. Because if you're getting that wrong, hopefully I'll explain something in a way that will help you figure out why it was wrong. But if you're just passively listening, you won't get that opportunity to have some magical video feedback. All right, so let's graph this. This is a greater than, and we've got a y-intercept of -1. We've got a slope of 2 over 1. So I'm going to go up 2 and right 1. This is supposed to be a dashed line because we're not equal to. So this is my line. Now we're going to graph greater than. So I guess this is kind of a line that I would say some of us might be having trouble with, because if you are confused about whether to think about x or y because there's both of them, you might pick the wrong thing. We want to pick a point on the line, draw up, and that's the side we're going to graph on because this is greater than. So we should be graphing here, right here. This is our shading where it should be. All right, example 5. We've got greater than or equal to. So equal to is going to be a normal line. We've got greater than, so we're going to shade above. We do have an x and a y, but we don't have a y-intercept. So let me just remind you that that would be a +0 at the end. And so our y-intercept is at 0. We're going to go -1 over 3 or 1 over -3, because those will give us actually the same thing, the same line. I guess they don't give us the same point, but they give us the same line, because we can go down 1 and right 3, which puts us here, or up 1 and left 3, which puts us here. In case it's not obvious, if you don't know how to graph, then graphing these is going to be a bit on the difficult side. So if I remember, I'll try to put a link in the description for just how to graph lines. So this is what our line looks like, and now we want to graph greater than or equal to. This is one that I think is relatively easy to see, because if we want to be greater than or equal to y, this is almost divided into a top half and a bottom half situation, right? So here's the top of our graph. That's where we're going to shade, because these are all the places where y is greater than or equal to -1/3 x. Last but certainly not least, example 6. We have y is less than or equal to 3/2 x plus 4. So we start with the y-intercept, which is at 4, and then we're going to do our slope, which is up 3 over 2, but wait, that doesn't fit on our graph. So remember that a positive slope, you can actually make both of them negative, because those two negatives would have canceled out, and draw the slope the other direction. So that would be down 3 and left 2. This is a solid line because we're equal to. And then we're going to say, okay, less than or equal to, I'm going to put my pin on my line and draw down for less than or equal to. And now I can see that this is the direction that I want to shade, right here. Isn't that shading beautiful? It's not really. I really like shading with pencil. It's not quite the same on the computer. Oh, I should have done beautiful. I should have done that the whole time. I'm so sorry that I deprived you of that on every single problem except for this one. Well, thanks for watching. This was a lot of fun. I hope you had fun too, or at least that it was not as not fun as it might have otherwise been. I hope that you'll subscribe if you haven't already, and like the video and all that jazz, and I'll see you in the next one. Thanks. Bye.